Hello everyone, today in this video we'll be discussing the fourth module of DSA, which is related to the continuation of trees from the third module, and we'll be learning about graphs. And make sure hit the like button, subscribe to my channel for more videos like this. And without wasting more time, let's get started and watch this video till the end. Easily you can score more than 80% marks. And let's get started. The first topic we have is the binary search tree. Totally 7 topics we have. We'll be covering each important concept from the exam point of view. So let's get started with the binary search tree, BST. What do you mean by binary search tree? Okay, see, there is a tree here which is having a root node here 25. Okay, and as you can see, all the nodes which are present here is greater than 5. Okay, so this is how we make the binary search tree. Now 25 less than 25 is 15, greater than 25 is 30. And if I want to insert another node, suppose 46 I want to insert, what I will check is 46 less than this or greater than this. It is greater than this, then I'll come to here. I'll check if it is less than this or greater than this. It is greater than this, I'll come here and check if it is less or greater. If it is greater, I will be inserting 46 here. Okay, like that. Suppose that I had to insert 32. Okay, what I will do, 32 and 25, it is the 25 is great, 32 is greater, 32 and 30, 32 is greater, and 32 is greater. I'll come here and see if it is greater than 45. No, it is not greater than 45. Then I'll come to the lesser side. This is the less side, this is the greater side. So I'll check 32 is greater than 33 or not. It is not greater, so I'll put it in the left side here. Okay, this is how the binary search tree is. Okay, some operations are there: searching, insertion, and deletion. Let's have a look. Searching a binary tree. Okay, very simple. A tree is a node which denotes the node of this tree, and the operation is search here. And tree root is taken into the parameters. So here the root is taken an int key which we want to search. Suppose that key is equal to 19. I have to search if 19 is present in that tree or not. First I will check if not root. If root is null, if root is null means this will become true, then return null means if root is null I cannot search anything. There is empty tree, if there is nothing to search, how can I search? So I'll return null. If it is if the root itself is the key, means the key I have to search, that will be root pointed to data. Okay, root arrow data, that means the data part of the root, whatever the root has, the pointer, the data part, if it is same as the key, that means I have to return the root itself, because I have found the key in the root only. If the key is less than root, if the key is less than root, I have to go to the left side, right? So what I will do, I'll again recursively call this same function, return search root comma left child, root arrow left child, and I'll pass the key here. Again it will call the same function with the left subtree of the root, and if it is greater, then I'll be calling it in this way. Okay, so if this does not happen, then it's obvious that it is not equal, it is not less than, the only option is it is greater than, so we will be greater than this. Okay, this is about searching binary tree. Suppose that I want to insert a node into a binary tree. Okay, so this is our binary tree. I want to insert 80. First I will check, is 30 greater or 80 greater? 80 is greater. So I'll check next, 40 is greater, 80 is greater, 80 is greater. So it's 80 is greater, I'll be inserting 80 here. Okay, that's what I did here. Next, insert 35. Now I'll check from here, 30 or 35, 35, 35 or 40, 40 is greater, so I have to insert into the left part. Okay, this is how insertion is done. This is a simple code here. Void insert node will take that node and the num which we want to insert here, and will create a pointer and a temp. Okay, two things will create here, pointer and temp. And temp will be having search node star comma num. See, in binary search tree we cannot have duplicate nodes, because it will again come into the same point and set. Suppose that again I want to insert 80, what will happen? I'll check 30 or 80, 80, 40 or 80, 80, 80 or 80, 80 or 80 means in the same node. Already 80 is present, why I want to insert another time 80? That is meaningless thing, right? So I'll check, I'll search if that num is present in the node tree or not. If it is there, it will come to temp. If it is not there, it will have null. So based on that, I will move further. Suppose that it was not there. If it was not there means here null will come. If null will come here, not of null means true. Then I will proceed with this. Num is not already present in the tree. Then what I will do, I'll take a pointer, create a new node, assign num to it, left and right child I'll make it as null. Okay, so my pointer is ready. I have to insert the pointer. Now if node is present, if root is there, means if there is empty tree means I can just um, do node star is equal to ptr. If it is an empty tree, I can just make the root node only as the new ptr. Else if it is not the it is not the empty tree, it has some values, then I have to check where I have to insert. If num is less than temp data, go to the left, else go to the right and insert it. Okay, next, deletion from a binary search tree. We have three cases. Okay, deletion means deleting any node. Okay, so first case is delete the node with no children. Suppose the tree given is this, and the node I want to delete is 66. Does 66 have any children? No, it does not have. So when I delete 66, what will happen? This will just get disappeared from here, and this will be the tree. Okay, that's all. Delete 33. Delete node with one child. See, 33 has one child, which is 25. If I delete 33, what will happen? 25 will come in this place. That's all. Okay. Delete 60. 60 if I have to delete, what I have to do here, tricky thing is there. Tricky thing, why? Because 60 has two children here. Okay, this is the third case. If there are two children, I have to find the in order successor. Okay, find the in order traversal of this tree and find what is coming after 60 in the in order traversal. What is coming after 16 in order traversal? That is 55. Okay, that's calculated, so I am telling here. But if you do it and calculate, you'll get the same answer. I'll get here 55. All you have to do is replace 60 with 55. In order successor you have to put here. That's all. In order successor, when you put here, what will happen? 55 has 52. 52 will come here. It is greater than 50. It will replace in the 55's place, and rest of the things will remain same. Here it is 45, not 55. Okay, 45 here. Okay, so rest of the thing will remain same. Whenever I get an in order successor, put that in order successor here, and the other children which is present here, put it here. If there are two more children, again find the in order successor and put it here. So it is a recursive function. Okay. That was about the binary search tree. Moving on, you have a selection tree. What do you mean by a selection tree? See, selection tree, first in the exam you will be given this, and either you will be asked to find out the winner or you will be asked to find out the loser. Okay, and they'll also tell you if it is a max winner or max or min winner. Okay, there are two types of winner and loser, max and min. Okay, based on that you have to proceed. So in this problem I'll be discussing the min winner. Okay, min winner. Let's have a look what is a min winner. Now this is given to us. Okay, these things are given, and these are the nodes, the top nodes which are present here. Okay, initially 10 will also be present here. We have to push it here and make it in the form of node. Okay, so 10, 9, 26, 8, 9, 90, 17. I have to find out the min winner. Okay, min winner means first consider these two, which is the minimum value, put here. Consider these two, minimum value, minimum value, minimum value. After you have done that, repeat minimum value and minimum value. You will get two answers. Minimum value which is there, this is the winner. Okay, if they ask you min winner, you have to take the minimum values and find out the winner. If they ask you the max winner, find out the maximum value among these two and then find out the winner. Now after you have done this one, you have got a winner. What you have to do is you have to reconstruct the tree. Okay, now what all other elements are present here, those are all losers. Okay, those are all losers. Now how do we construct a loser tree? Okay, see, 6 is winner, so we have to eliminate 6. Now the remaining elements are the loser elements. Now what we will do is, wherever 6 is there, first we erase that. Okay, now we are constructing a loser tree. 6 is the winner, we have got to know. Now we are constructing a loser tree. Okay, just a second. Okay, now 6 is also present here. We will be removing this. Okay, now see, 6 is also present here. I have to remove this one. Now see, here 15 is present, right? So I have to put here 15. Okay, after putting here 15, what I will do is the remaining ones, I believe it was 28. Okay, it was 4 elements here. Okay, now see, 15, now 15 or 20, which is lesser. Lesser is 15. I'll put 15 here. 9 or 15, which is lesser. 9 is lesser. 9 or 8, 8 is lesser, so I'll put here. Now this tree which I have found, this is called as a loser tree. This whole tree is called as a loser tree, and I have to put 6 here, which is the overall winner. I have to write like this, overall winner. Okay, this is about the selection tree. The next topic is the forests. Okay, so what do you mean by forest? How do we form a forest from a binary tree? Removing the node of a binary tree gives us a forest of two trees. Okay, so see here, this is a binary tree. If I remove 60 from here, I'll be remaining with two trees, which is, this is first tree, this is second tree. Okay, so this is called as a forest. This is called as a forest. Multiple binary trees form forest. Okay, So forest can be converted back to binary tree by joining the two roots to a single node. Now if I have these trees here, I'll join it using a single node. That will form again a binary tree. Okay, and pre-order, in order, and post-order traversals is same as in the previous ones which I discussed in the previous modules. The traversals, same thing applies here also. First we'll traverse this, we'll traverse this, like that. Okay, that was about the forest. Next is representation of disjoint sets. Okay, suppose that we have 10 elements. How many elements we have? 10 elements, 0 to 9, and we may portion them into three disjoint sets. 0 to 9, I can take set 1 as 0 6 7 8, second set 1 4 9, and third set as 2 3 5. This is called as disjoint sets. Okay, now this can be represented as like this in the form of a tree. Okay, 6 7 8 pointing to 0. You can take anything, you can put 6 here and put 0 7 8, like that. You can do anything, just it should be in the form of a tree. Okay, so three trees will be there, s1 s2 and s3. Okay, and if you want to find out the union, this is an important operation, s1 union s2. Okay, how we'll find out the union? Now suppose I want to find out the union of s1 and s2. Okay, first you say me which has more nodes, s1 or s2. S1 has more nodes, it has 4 nodes here, it has 3 nodes here. So when we do s1 union s2, what will happen is this one will be pointed like this. Okay, see, this one will be pointed like this. Whichever has greater nodes, that will become parent, lesser nodes will become children. That is using weighting rule. Okay, and data representation of s1 s2 s3, s1 s2 s3 will be here, and the pointers for those respective ones will be pointing to the three trees. Okay. Another operation is the find I operation. What does find I do? It returns the root of the set in which I is present. Okay, so I told you, right, this is a set. Okay, this all are sets. Three sets are there. We have s1 s2 s3. Now suppose I tell you to give me the root of 5. For root of 5, first you have to construct this tree here. And what is 5 pointing to? Means the root of 5 is 2. 5 is pointing to 2. So 2 is the root of 5. So if I find I, instead of I put 5 here. Like find 5. It will return me 2 because 2 is the root of 5. Okay, got it. That's how the find operation works. So this is the code here. We'll use a for loop here. Parent of I till it is greater than or equal to 0, we will continue. I is equal to parent of I. I will become parent of I. Okay. So suppose that here 6 was there. If I want to find 6, okay, find 6, how will do? Find 6 means I is equal to parent of I. What is parent of 6? Parent of 6 is 5. So I will become 5. Then what is parent of 5? Parent of 5 is 2. So I will become 2. Like that I'll continue till I reach the end, and when this gets over, then I will return I, which means that my answer is the root. Okay, and for union, we'll take two vertices here, I and j, whichever has greater nodes. We are not checking here, but that's how it works. Here we have directly written parent of I is equal to j. Supposing that I has more nodes and j has less nodes, if you are following the weighting rule. Okay, so parent of I will make it as j. Okay. Next topic is the counting binary trees. Okay, here we have the applications of binary trees. Okay, we have the applications. Now, the first application is distinct binary tree. Suppose that n is equal to 2. If there are two nodes, it can be either like this, having a left child, or it can be having a right child. That is the two distinct binary trees. If n is 3, we have 5 distinct binary trees with 3 nodes. Okay, that is the first application of counting binary tree, which is distinct binary tree. Second is stack permutation. In the previous module, we had discussed that if pre-order and in-order is given, okay, this is the pre-order traversal and this is the in-order traversal of a tree, we can construct a binary tree. How do we construct that? In pre-order traversal, we know that it is NLR, node left right. Okay, for each node it is in the form NLR. When we are traversing the tree, first we'll do N, then we'll go to the left, again NLR, and again NLR. Like that we used to do, right? Traversal, if you haven't seen the previous module, first was that. Okay, then you will understand what I'm telling. Here NLR is used in the pre-order. So based on that, A will be the root node because it's starting from A and it is NLR, means first we are printing the root node only. That's how we get to know that A is the root node. Okay, after that in order it is LNR, means the nodes left part and the right part will be like this. Okay, first A is the root node, we got to know. So when we do L and R in the in order traversal, first we'll travel to the left, and when left part is over, then we'll print the node and then we'll go to the right part. So we know that A is the root node, right? If A is the root node, that means that left part of A is the left part and right part of the A is right part, right subtree. So A is the root, it can be divided here. BC is the left part and EFGHI is the right part. Okay, so this is how we do the this is the second application of counting binary tree, which is stack permutations. Okay, Next is matrix multiplication. Okay, so if n is equal to 3, there are two possibilities. It can be either m1 into m2 into m3 or m1 into m2 into m3. Okay, if n is 4, there will be 5 possibilities. Okay, so what we can observe is the number of distinct ways is equal to sum of all possible binary trees. Okay, with a root and a subtrees, two subtrees, one root and two subtrees, pi and b n minus I minus 1. Okay, so here some formulas are given. Based on this formula, we can calculate how many ways are present. That will be equal to the number of binary trees with n nodes. That is equal to number of ways of multiplying n plus 1 matrices. So what we are trying to do is representing the matrices in the form of nodes and finding out how many binary trees can be possible. That is equivalent to our answer, which is number of ways of multiplying matrices. Okay. Next is number of distinct binary trees. The binary trees can be duplicate also. So we have to find out how many distinct binary trees are there. For that, some mathematical calculations are present here. So we need to solve the following equation of Bn, and we'll be assuming Bx is equal to the summation of Bixi for generating the binary tree. And by recurrence relation, we get the identity, the following identity. Then after that, we will use the quadratic equation. So we'll be obtaining this formula here, and when we apply the binomial theorem on 1 minus 4x power 1 by 2, we are applying the binomial theorem on this part. We will be obtaining the following equation, and further simplification will be getting this. You need not memorize this one, it is just for your information. In the exam also, they will not ask in this much depth. You just have to mention that the following are the applications of binary tree. We can find out an number of distinct binary tree. We can find out the matrix multiplication, how many possible ways are there. We can find out the distinct binary trees, and we can find out the stack permutations. Okay, you just have to mention the applications. Okay, and if you can, whatever you remember, that also you write in exam. Okay, moving on to the second half of the module, which is about the graphs. Introduction to graph. What is a graph? It's the same as a tree, but it can have a cycle as well. Okay, so let's discuss what is a graph. G is equal to v comma e. This is how we represent a graph. G for graph, v for vertices, e for edges. Okay, so this is a vertices, 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 vertices. All these are vertices. The lines are the edges. Okay, these are the edges, and we have two types of graphs: undirected graph and directed graph. Undirected graph means there will be just a edge here without any direction. Okay, so it will be connected in both ways. It is bidirectional. Okay, there is no specific direction. Directed graph means there is edge only in this direction. The other edge in other direction there is no edge. In this way, there are both edges present. So there is no specific representation of the direction. Okay, so we have two types here: undirected and direct graph. Now graph can be represented using adjacency matrix or adjacency list. Let's have a look how does that happen. Suppose that there is a graph G in which 1 2 4 and 3, there are 4 vertices, and 1 2 3 4 4 edges are there. Okay, now if you want to represent this using adjacency matrix, what you have to do is 1 2 3 4 is there, right? So we'll write 1 2 3 4 here and here also in the rows and the columns. Now if it is a unidirected, means undirected graph, 1 to 2 also there is an edge, 2 to 1 also there is an edge. It is bidirectional. Okay, if there is nothing specified here. So 1 to 2 and 2 to 1. So here 1 to 1 there will be no self loop here. Okay, so always 1 to 1 it will be 0, 2 to 2 it will be 0, 3 to 3, 4 to 4. Itself there is a no loop here, right? So there is no edge present, so that will be 0. Now from 1 to 2, is there an edge? Yes, there is an edge. I'll put it as 1 here. 1 to 3, is there an edge? No, it is not there, so I'll put as 0. 1 to 4, is there an edge? Yes, it is there. I'll put it as 1. Now 2 to 1, 2 to 1 also there is an edge. It is bidirectional. If it was unidirectional, suppose that instead of this it was like this. Okay, it was like this. 1 to 2 only it is there, 2 to 1 it is not there. So here 2 to 1 I would have put as 0. Why? Because it was only in one direction, but here it is double direction, so we need not will be having to mention both 2 to 1 and 1 to 2 as 1. So 1 denotes if there is an edge, and 0 denotes if there is no edge. Okay, now this is adjacency matrix. Another way of representing it is in the form of adjacency list. Here just note down 1 2 3 4 here as such, 1 2 3 4, and from 1 you have an edge to 2, edge to 4, right? So 1 to 2, 2 to 4, like that. It will not mean that 2 to 4 there is an edge. It will be 1 to 2 and 1 also has with 4. Okay, like that. And similarly for 2 also, for from 2 it is connected with 1 and it is connected with 4, so I'll write here 1 and 4 in that order. Okay, and 3 is connected with 4, so I'll write here 4 is connected with 1 2 and 3, so I'll write 4 with 1 2 and 3. Okay, so this is another way of representing the graph. Okay, Moving on to the last topic, which is graph operations. There are two search operations on graph, DFS and BFS. Okay, so search operation means this is a graph given. I want to search an element in that. Okay, so that is what my operation is. I have to use either of two operations. The first one is DFS, depth first search, and second one is BFS, breadth first search. Okay, so let's understand the difference between them. In depth first search, I'll be starting from the first node here. Suppose that 2 is my first node, and here I'll be using stack. Okay, stack I'll be using, which is the leaf hole, last in first out. You'll understand why I'm using a stack here. Okay, so I'll start from 2 here. Okay, you can start with any node, or if they mention any node, you have to start from there. Okay, I'll start from 2 here. So first I encounter 2, I'll be writing 2 here. Next, after that, go to the any next node here. For 2, only one node is there, so I'll be writing here 1. Okay, next, after 1 I have 5 and 3. I can choose any one. I'll choose 5 and I'll go with 5. Okay, after 5 again I have option 4 here, so I'll go with 4. And from 4 I have two options, 6 or 7. I can go with any. I'll go with 6. After I've gone with 6, is there any other option? No. If there is no other option, pop the element, pop 6 from the stack. And what is below 6? Below 6 is 4, so check 4 if it is having any other node which is unvisited. Yes, 7 is there, so then push 7. From 7, 8 is there, push 8. Then from 8 nothing is there, pop 8, pop 7, pop 4 also, because 4 has 6 and 7 which are already visited. After popping 4, what you had here, 5. Now you check 5. 5, 4 is visited, again pop 5, and you'll come to 1. From 1 I have 3 here, right? So I'll be visiting 3 here, like that. Okay, after that, pop 3, pop 1, and pop 2. So all the nodes are visited here. You could have done in this way also. After you have come from 6, again you came back to 4. I had another option, 7, 8. Okay, 7, 8 I have visited here. I'll come back here to 4. 6 is visited, 7 is visited, and from 4 I had 3 also. You could have gone like this also. Okay, that is also possible. From 4, if you go to 3, 3 will be visited. A different answer you will get, but both are valid answers. Okay, so here, since we are doing the pop and push operation, whenever we are going, first we will go to the end, come back. Okay, that is what it is, depth first search. First you have to go till the end, then come back. Okay, so this is the depth first search. You'll be using stack here. Okay, let's go to the code here. So this is void DFS. Will be accepting a graph here, and will be accepting a vertex. Okay, vertex, and will be accepting a graph here. Two things we are accepting. Graph is the one which we have, this one, and vertex is the one which we are try to find out. If you want to find out 4, if you want to find out 7 is there or not, 8 is there or not, like that we are accepting in the vertex. Now graph of visited vertex is equal to 1. See, we have the visited of vertex is equal to 1. We'll be first marking the visited vertex as 1, so vertex will be visited here. Okay, next, node start time. We are taking a temporary pointer here, and that temporary pointer will be assigned the adjacency lists of the vertex. Okay, suppose that I had 1 here. Adjacency list of 1 will be 5 and 3, because 5 and 3 is connected with 1. Okay, 1 I'll mark it as visited. This is visited, then I have to visit 5 and 3 one by one. Okay, so that will be in the temp. The whole list will be there in the temp, which will be having 5 comma 3, like that. Okay, now while temp means while 5 and 3 present in the list, what I have to do, I have to take the first one, and then I have to mark it as 0. This is not visited, and I have to pass that vertex into the graph again, DFS. So I'll consider any one of them, 5 or 3, and then I will send this back to the same function, so that this will be marked as 1, and I'll come here again, recursively call it. This will be marked as 1, like that. I'll keep on going until I reach the end. When I reach the end, I'll come back here. This is done, I'll go to the next one. Okay, if from the adjacency list, if 1 is done, I'll go to the next one, while temp, right? So temp or arrow next. So temp arrow next will lead me to 5 is 5 is over. Temp arrow next will lead me to 3. Like that, I'll keep on doing all of it one by one, and I'll be noting down the answer here. Okay, so this is the code for DFS. Next we have the BFS, breadth first search. In breadth first search, what we will do, first we will visit all the adjacency vertices. Okay, what we will do, first we will visit all the adjacency vertices, and here we'll be using a queue. Okay, why we are using a queue? Because it is first in first out. Okay, while we visit all the adjacency vertices, we have to come back again. Okay, we are not going back again till the end. Okay, this is breadth first search. We are visiting all the adjacent vertices. Let's understand this using an example. 2. First I'll visit 2 here. What is the adjacency of 2? Adjacency of 2 is 1. 1 is connected there. I'll visit 1. After 1, I'll come back to 2 and see if anything more is there. No, it's not there. Then I'll come back here, 1. From 1 I have 5 and 3. I have 5, I have 3. I visited 5, I visited 3. Then I'll choose either 5 or 3. because once all vertices are visited, I will remove it. Next, I have 5 or 3. I can choose any of them. If I choose 5 here, I'll choose 5. What is the adjacent elements of 5? I have 4 here, so I'll be writing here 4. Okay, then after that 5 adjacency is over, I'll come to next, which is 3. Okay, that's why we are using first in first out. First in first out, then it was this in, then it will be this out, then it was this in, it will be this out, like that. Okay, in that order we are going. So after 5 is done, once another neighbor was 3. Now I'll visit check for 3, which is the neighbors. 3 has 4. 4 is already done, so we'll not do anything. We'll remove 3 also. Okay. Next we have in the list we have 4 here. Now 4 has 6 and 7. I'll write here 6 and 7. Now 4 is done. Now I can choose 6 or 7. I can choose any of them. I'll choose 6. 6 is done here. Nothing else is there. I'll come back and I'll choose the next neighbor of 4, which is 7. Next number of 4 is 7. 7 has one neighbor, which is 8. Then I'll write here as 8. And 7 does not have any other neighbor. I'll come back. 4 also does not have any neighbor. I'll go for 8. 8, does 8 have any neighbor? No, it does not have any neighbor. So 8 is also done. In this way, when we traverse finding out the adjacent vertices, we will not move next level until all the adjacent vertices of this element is covered. We will not move to 4 until 5 and 3 is covered. Okay, we have visited 5, visited 3, and find out the adjacent elements. Till then we will not take any of the adjacent elements of 5. Okay, that is how breadth first search works. In this way also, the same thing is present in the code also. I'll give you a glance. So see here, we are accepting a graph and a start vertex where you have to start it. We are using a queue, front and rear. We use a front and rear in the queue, right? So graph of visited start vertex will be equal to 1, and in the queue we will be inserting the start vertex because it's visited. While front is less than rear, current vertex take the element which is present in queue in the first place as current vertex and mark it as visited. Next, take a temporary pointer and take the adjacency list of current vertex. Means whatever the current vertex is pointing to, that all elements I'll be taking in temp. Okay, so again temp will have 5 comma 3. Now while temp is present here, take adjacent any adjacent vertex of temp and then mark. If it is not visited, mark it as visited and insert that element in the queue. Okay, that's what we are doing, right? See, we are visiting here, marking this element as visited and inserting it to the queue, and then visiting this one and putting into the queue. After that is done, after all the elements are done, temp will go to the next one. Next one is 5 here. 5's adjacent element will be put into the matrix and then we'll again come back here. Now we'll visit 3. 3's adjacent matrix is already present 4 here, will not do anything. We'll mark 5 and 3 as done. We'll move to 4. Next again the same thing will repeat. 6 and 7 we will take. 6 and 7 we will insert. Like that we'll keep on inserting and keep on going to the next temp arrow next, and we'll be visiting all them in the form of BFS, which is breadth first search. First adjacent elements, then we'll move to the next level. Okay, that is very important. The code and the means how it works. You can expect both type of question in the exam. Okay, same thing you have to do whatever I have done in this explanation. Okay, moving on, we have the spanning trees. What do you mean by spanning tree? This is the last topic. So a spanning tree is a tree which has n. A tree can have n minus 1 spanning trees. Okay, so let's understand what is a spanning tree. Okay, so let's take a graph here. Okay, in this graph there are 4 vertices and all are connected. Now how many edges I can remove and still have all the vertex connected? Listen to me again. How many vertex can I remove and still have all the vertex connected? See, I can remove the x in between and this also, and still I'll have a connected graph. I can remove this one and I can remove this one. I can form a line like this and like this, and I can still have a graph like this. Okay, so that is what is called as the spanning tree. How many such trees I can form? If there are n nodes, I can form n minus 1 spanning trees. See here 4 nodes are there, so I can form 3 nodes. Means 3 spanning trees I can form. First spanning tree, second spanning tree, third spanning tree. Apart from this, there is no other spanning tree which can exist, which can connect all the nodes. Okay, that was about the spanning trees. And if you found this video helpful, and please like, share and subscribe, and thank you so much for watching. I'll see you in the next one.